Hello everyone. I hope you can hear me well. I'm honored to present here today. My name is Lucas, and today I will be presenting a castle building tool that I've made as part of my school project earlier this year. The purpose of the project was to initially create a versatile tower generating tool, but then it evolved into something more, which is a fully fledged castle building tool. So let's start. First, I'd like to go over some basics. So I started to create my tower generator tool in Houdini, where I made some basic structure generation and some customizations with parameters. Then I ported the tower into Unreal Engine through HDA, where I can then utilize and instantiate multiple different towers. Then I built the whole castle by combining the towers together, and I added some textures, some landscape, and some trees. So let's go over the pipeline. The basic tower generation is pretty straightforward. It starts by just extruding it from bottom to top, which is directed through parameters. And it is divided into 4 parts that are color-coded, and each part represents a section of the tower that you can edit. For the tower customizations, here are some examples showcasing the versatility of the tool. To achieve maximum flexibility, I exposed more than 100 editable parameters to the user. Some of the parameters are choice of a roof or a battlement, shape of the section, number of windows or arrow slits on the tower, or width and height of each section. With this tool, you can create almost any kind of tower that you can imagine as long as it's symmetrical. The idea to evolve this into something more came to me with this reference. Oh, sorry, it should be like this, yes, sorry. So the idea came to me with this reference that I found on the internet, and I realized I could build something more with the tool than just a single tower. This created some more challenges. As I tested the idea, you can see that my tool didn't work as well. Indicated by the red arrow, it didn't support inverted base. So I quickly made some iterations to my ramp node, and then it started working again. So for the reference, to demonstrate the usability of the tool, I wanted to take it one step further and construct a whole castle. I was looking for some references, and I stumbled upon this Butron castle, which is located in Spain. And that was exactly what I was looking for. In essence, the castle is basically compiled from a bunch of towers, and that made it much easier for me to use just that single tool to create the whole castle. So I obviously cannot show you the whole building process because that's hours of footage, but I wanted to include a sneak peek of how it looks when you're working with the tool in Engine. You must be quite creative when you use the tool because it has a lot of capabilities with regards to customization. And you can create almost any kind of tower. In this example, I'm actually putting 2 tower instances on top of each other to create a tower from the reference, which is highlighted in the red square. To show the process of building the castle, I decided to make a compilation of different stages of the build. Those stages show more or less how I proceeded from start to the end. You can notice that 2 parts in the end are not made procedurally. Those are the chapel and the bridge. So here are some images where you can see the final result of the castle after applying some quick textures, materials, and placing it into environment with the help of PCG in Unreal Engine. And I also tried some different scenery, placing it on top of a cliff, and that turned quite nicely as well. And here you can see a short turntable of the castle. So I always like to reflect on my development, and if I would like to enhance this project in the future, I think it could use some better interface to enhance the user experience, especially since it has so many parameters. This could be done either through scriptable tools or editor utility widgets in Unreal Engine. Lastly, I think the UV mapping could be a bit more complex to break up the tiling of the textures. Thank you so much for listening. If you have any questions, you can reach out to me either on my socials or later afterwards this talk. I am also open for internship offers starting this September, so feel free to reach to me. Thank you.
Hello, everyone. It's a real pleasure to be here today. Such a nice conference. My name is Mace, and today I want to present with you my small showcase of the garden generator I did within the Unreal PCG framework. At its core, the garden generator operates on two spline components, the edge spline and the path spline. Additionally, I leveraged pack level instance. For those unfamiliar, pack levels function like prefabs, allowing you to create a custom container that holds geometry, which can then be instanced throughout the level. Within the first component, I'm using just the edge spline to place the border walls and the basic ground coverage. Based on a simple curvature filter, I place either a straight or a grounded wall level instance. This method is not only efficient, but also very flexible within PCG, as we can tag, filter, and modify meshes inside each instance after they got placed. For example, here you can see what I do after the curvature filter. With the placed stairs, with the placed straight wall, I filter for the tagged shrubs only and mask them out wherever the stairs bounding box is overlapping, while keeping the stone wall still in place. Every shrub which is still placed is then randomly transformed a bit to give it a more variation across the board. Let's move on to the flower scattering. For this component, I'm using the edge spline and the path spline. First, I delete all the points which are inside the spline bounding box. Then I compute the distance to the path spline on the surface. And then I compute the distance, which can be visualized here as a density. With this density information, I can now instance different flower categories. I have 3 flower categories, white, red, and purple. By aligning the height of the spline, I can define the flower type, but also scale based on the distance towards the spline. Let's move on to the stair component. Here we are using the edge spline and the path spline again. First, I filter out all overlapping points of both splines. These filtered points are then injected into a custom PCG blueprint, which acts like an attribute transfer node. Since the setup has never been shown before, I would like to walk you through what it requires to make such a custom blueprint. It's getting a bit technical, but please bear with me. First, we have to set up and declare the input data information. I have 2 input pins, the border and the path points. Then we have to initialize and store each point data. This process is what Epic called as a boilerplate setup, which is needed for any kind of point data manipulation. Now I want to get the closest point. First, I get all vector positions for each border points, as you can see on the top right. After that, I run through each point on the path and check the distance against the stored border point's position. This is what the blueprint looks inside. I define the max search radius and test for each vector the distance. There will be only one point, which is the closest, and I get this index value, and store this index inside a new array on the same index of the current path point operation. Finally, I can loop over each target point data. I get the length of the target point array as the number of iterations, and now we are inside the loop body. For each point, I get the corresponding closest index as stored before. I then check the orientation axis with a dot product. We can visualize that nicely with an Unreal debugger view. On the left, we can see how the red x-axis on the border points are orientated in the opposite direction as the path point. In this case, the dot product is negative, so I rotate the jaw about 180 degrees. Then I have to make the actual new point data and output it for all the points. I get the point location of the border spline, and depending on the dot product, I flip the jaw. So let's see it in action. We can now draw the path spline, and on the edge spline, we are automatically placing the stairs, which are also using the jaw rotation of the path spline to flow nicely within the path. Then That was quite a ride for an attribute transfer. And at this point, I was wondering how would this setup look inside Houdini. So I made a small test. Everything you just saw in the custom blueprint setup fits within this attribute wrangle. I'm using just an XYZ distance together with a prim UV and make the same operation with a dot product and align the orientation about it. Let's go briefly over the last component. The main concept here is that I solve for the intersection and use a mesh array to instance different types of stone passes and step rotate them to give more variation. As my time is running out, I would refer you to my 80-level article about the system, where I explain more about the custom blueprint setup I used for this component. I want to wrap it up with 2 tips. If you want to learn more about custom blueprint setups, I can recommend the folder BP Elements inside the PCG plugin, which still contains all the initial custom blueprints made by Epi Games for the electric beam sample. Especially the deprecated folder is very useful to learn from. And another small material trick, the speed tree color variation material function, which is standard in Unreal, can be used to get a nice variation for every instanced mesh across the board. That was it. Thank you for listening. I'm also on the lookout for job opportunities. Please feel free to reach out on me on LinkedIn, the link tree on the side, and if you have any questions, let's have a chat later. Thank you.
Hi, and welcome to my talk about Delaunay pattern generation. My name is David. I'm a third-year visual arts student here at BUas, and I've been focusing on Houdini and procedural generation mainly since the start of the second year. To begin with, what is Delaunay triangulation? I'm sure a lot of people here are already familiar with this, but for those like me at the beginning of this project who aren't, here's a quick overview. Given a set of vertices, Delaunay is a method of triangulation in which none of the vertices fall within the circumcircle of a triangle. What does this mean? Well, this is useful because it is a way of creating non-intersecting triangulation. And as a bonus, it also tends to avoid sliver triangles unless necessary. Well, why am I talking about this? For me, this project started out mainly as a learning exercise in VEX, with the goal being to implement an algorithm to create the Delaunay triangulation. As someone who doesn't usually do much coding, it was nice to challenge myself to do something on the more algorithmic side and just generally familiarize myself more with VEX. Next, I'll give a quick overview of how the Boyer-Watson algorithm used to create the triangulation works. Here we have the initial point set we're trying to triangulate. The first step is to create the super triangle, which encases all of these initial points. Next, we can arbitrarily pick the first point and connect it to the vertices of the initial triangle. This in turn creates 3 new triangles. When adding the next point, we now need to check for each triangle whether the new point is contained within its circumcircle. If not, this triangle is considered valid, such as in this case. The same goes for this circle, but in this case, the evaluated triangle is invalid. What we do then is find the borders of the invalid triangle. In this case, it is only 1, although it can also be multiple. And then we connect the vertices to the newly added point, creating a new valid set of triangles. This process is then repeated until we have iterated through every point, arriving at the final triangulation. For the sake of brevity, and maybe also your sanity, I will spare you the horrors that is my VEX code. But here's what I got in Houdini, with the points being scattered on the grid and run through a wrangle. As you can see, the triangulation works and updates to the scattering or when a point is moved through it. As a note, there's also a native Houdini node called the Voronoi adjacency, which will give you the same output. I use this to check my code against and see if it works correctly. So this is kind of cool, but what are ways to make this visually interesting? Well, the easiest way is to control the scattering of the points. Here I grabbed an image of Shutterstock, mapped it to a grid, and then scattered points based on the color density, which I think already looks way more intriguing. In my mind, the next logical step was to make it move instead of simply having a static image. So to animate it, the initial points are piped into a basic infection solver. One point is selected as the origin and given an infection attribute. In the solver, every point which has this attribute finds the nearest uninfected point, and then passes it on. The solver then runs this per frame, with the previous output being used as the starting point for the next frame. After deleting all the non-infected points and running it through triangulation, this is the result. Then I try to experiment by manipulating the motion of the points. Here I increase the amount of frames between steps in the solver, isolated the newest iteration and its predecessor using time shifts, and then blend between them using a sequence blend. And this is how it looks when applied to an image. Since the blending happens between different amounts of points, the point ordering also changes, making the result a bit chaotic, though I also find it interesting how parts of the image kind of move together in a wave-like fashion. Another effect I tried was to grow the edge. To do this, I modified the solver to add an additional age attribute to each new iteration. This way, the edge can be isolated by deleting every point except the newest ones, which are then triangulated, put into a carve, and merged back with the rest. Lastly, I also experimented with ways of dissolving the image, simply by selecting random vertices in a group range and deleting them. In the top example, this is done after the triangulation has occurred, whereas in the bottom one, it is done before. To add some more interest, I also controlled the affected area by only selecting from a group within a bounding region, which is just based on keyframe geometry. The main takeaways for me on this project, besides learning Vex, were the fun I had with experimenting. This project didn't start out with an end goal in mind, and I think it speaks to the power of Houdini and proceduralism as a whole, and how quickly interesting visuals can be created through simple interactions. That being said, thank you for your time and attention, and I hope you enjoy the rest of the talks. Thank you.
Hello, and welcome to our presentation. My name is Santiago, and this is Ferry, and we're both Year 2 programming students here at BUas. And for the last 8 weeks, we worked on an engine that uses procedural tools to create natural landscapes, and that is what we will be presenting today. So let's dive right in. So Blossom is a custom game engine developed by us two along with 3 other colleagues, with the specific aim of being a nature simulator. And by embracing a procedural workflow, we've created a fast and efficient tool for creating scenes like this. There was a key focus on developing robust tooling, giving the user great flexibility and range to use the engine. Furthermore, we've incorporated simulated geometry for grass, wind effects, and interactive elements. And this video here demonstrates usage of the engine to create a small demo scene. But we'll see more of that later. To design a procedural content creation tool, we decided to allow the user to just use noise textures to edit the environment and placement of objects. This creates a pretty simple editing dynamic, since all you need to generate a level is texture input, some scalar configurations in the engine, as well as models for the props. And the props are trees, rocks, flowers, bushes. We integrated a noise node editor into our engine, originally from the Fast Noise tool library, which is open source. This noise editor allows combining noise textures in many creative ways and allows exporting it to a file, which can then be used in the engine. This kind of enables a user to effectively create noise textures within the engine and without the need of an external tool. Going into more detail, the way our engine places props around the scene is actually very simple. First, we generate a set of points using Poisson disk sampling, which creates this nice uniform distribution that has this minimum spacing constraint, so you don't get overlapping points. After these points, we apply a density map noise texture, which discards these points based on their position. So a value of white means the points completely pass, and black means that they don't. Finally, we then adjust all of these points to the correct height on the height map that dictates the actual heights in the scene. And then we add some random rotation and variable size to each object to add some variety. Lastly, then we just pick a prop model pool from the random prop pool that we have for all of our props. So for example, a tree can have many different model variations. So we pick a random tree model and then we instance it along the field. This right here is the final output for instancing a bunch of trees. And I'm going to leave you with Ferry now.
Grass plays a crucial role in enhancing both our engine's immersiveness and the visual appeal of our scenes. By integrating simulated geometry, we breathe life into our environments, creating a more immersive, natural experience. Our objectives included rendering vast quantities of grass, enabling player interaction, simulating ambient wind, and seamlessly integrating with the environment. Leveraging our noise workflow, we achieve precise control over grass density across landscapes, while also refining generation of our wind effects. In ensuring seamless integration with the environment, we utilize the height map associated with the terrain to align each grass blade with its corresponding elevation. Additionally, a length map governs the dimensions of the grass, allowing for the creation of patches of sparse areas to tailor to the landscape's appearance. Furthermore, a color map comes into play. While opting for stylistic flat shading for the grass blades, we aim for diversity within each blade's appearance. The color map enables us to dynamically sample colors based on the grass blade's position on the terrain. Each grass blade possesses 2 degrees of freedom in its movement, allowing it to sway forwards, backwards, and sideways. These movements controls play a crucial role in simulating wind effects across the landscape. Our approach involves utilizing a Perlin noise texture to generate ambient winds, which we dynamically scroll over time. Furthermore, we offer global controls for adjusting the wind's direction and speed. Collectively, these variables come together to dictate the direction and intensity of movement for each grass blade. In our pursuit of enhancing world interactivity, we aim to enable player influence on the grass as they traverse through the environment. To achieve this, we implement the displacement map mechanism. As the player moves, their speed and distance from the terrain dynamically alter this map. The resultant push data is encoded into the texture, ready for interpretation by the grass. Subsequently, the grass utilizes this information to determine both the direction and magnitude of the applied force. Finally, we can put all these elements together, both the grass and the editor toolchain, to create a nature landscape. You can see in this video, I'm creating a noise map that will be used as the height map for the terrain. I then use that same noise map and apply some extra effects to generate the grass length map. I will then use the grass length map to create a density map for the flowers, so the flowers will only be placed in the grassy areas. I then use the same map, but this time to place birch trees. Then I invert the grass length map and use that map to place pine trees and rocks in the dirt area. Afterwards, I create a mask that simply contains a dot in the center, which will be used to place some houses. Finally, I modify some of our lighting settings, like the bloom and the skybox, to finish the scene. This toolchain allows us to completely create this scene from scratch in our engine. Thank you for listening to our presentation. Here are our socials if you want to reach out to us, and we hope you found the presentation interesting.
Hi everyone, my name is Sahar. I'm a second-year student here at BUas, and today I'll be presenting a tool that I developed for procedural generation of jellyfish, and this project was completed over a course of 2 months. This tool was entirely created in Houdini. The geometry, textures, and animations are fully procedurally generated. I will now try to explain how I did all this work in the short time that I have. Starting with the jellyfish geometry, I broke it down in 4 main parts: the bell, the oral arms, and the internal organs, and the tentacles. Everything is set up so that all these parts all depend on the bell design and movement. As we can see here, I have implemented a lot of controls over the geometry and the simulation. Once the user is satisfied with the setting, each part can be cached separately. And after designing the bell, we can create various modular parts and assemble them together. So for example, with 3 variations for each component, the oral arms, the tentacles, and the internal organs, we can achieve around 27 unique combinations. This modular approach allows us to achieve a wide variety of looks with just a few assets. So this makes it easier and efficient to create realistic scenes filled with many distinct jellyfishes. And now for the simulation part, which are the oral arms and the tentacles, I'm using vellum close simulation. I set the gravity in the solver to a very small value so that we can get this floaty underwater motion. I also use color masking to segment different areas of the mesh, and then of the different areas of the mesh that I want to have different values for the stretch stiffness, bend stiffness, and such. Considering that the jellyfish don't have bones, I went with a procedural method instead of the usual mesh modeling and rigging. This way I prevent the usual restriction that comes with a fixed rig, and also get way more flexibility to tweak the geometry and animation as I go. The creation process begins with a simple line. The line then is animated using a bend node, but rather than manually keyframing the bend node, I'm dynamically controlling the animation using an attribute, which is built in a motion graph developed in a chop network. This setup allows complete control over the jellyfish animation dynamics, like the speed and the degree of the bell contraction and expansion. For the animation along a path, I calculate the velocity using the height of the bell at any given time. This way, I synchronize the movement along the path with the bell animation. So during the contraction, it moves forward, and during the expansion, it slows down. To get the bell to follow the path, for every frame, I carve along the path guided by this velocity attribute. The final travel distance per contraction is controllable through a multiplier. A jellyfish usually doesn't follow a regular swimming pattern. They're actually quite random. To simulate this, I design a system that switches randomly between swimming and idling for each animation cycle. So when the feature is activated, each individual jellyfish displays a unique animation pattern, which makes complex scenes more realistic. To make the procedural texture, I broke down the bell pattern into 3 key parameters: stripes, the bell dots, and the bell border. These are initially built as meshes, and then I project them onto the bell surface and transfer the color there. Each of these parts are then assigned to a RGB channel. This makes it easier to separate them later when I create the ID texture maps. For the other parts of the jellyfish, as you can see on the right side of the screen, I'm using color masking to divide different areas of the geometry. These parts are then coded into RGB channel in the same way. I'm also reusing the color mask information for other purposes, for example, for the volume simulation for the oral arms, as was mentioned before. For my render, once all the parts of the geometry are cached, I proceed to create the material and set up the scene. I render the jellyfish separately from the background, and I use Nuke for the compositing. For more detail about the project and quality render, please make sure to check out my art station, and thank you for your time.
Hello everyone, my name is Seb van der Beemt and I'm a third-year student here at BUas, and today I will be presenting my Procedural Destroyed Castle Wall Builder. So what this tool is a tool that allows you to draw a castle wall and dictate its destruction. So to give a quick overview of what it looks like is you first start off with a spline that allows you to draw out the main shape, and then you can add these things that I like to call destruction cubes, which, as the name implies, allow you to dictate where the destruction should occur. After that is done, you can bake it down to a mesh, where it will also apply some foliage on top of the wall. So before I started this project, I first started looking for references. My main reference is this castle in the UK called Beaumaris Castle. It really had interesting shapes, but in my opinion, it wasn't destroyed enough. It sounds kind of harsh, but it didn't have the interesting destruction shapes I was looking for. So for that reason, I looked further and found another castle called Carisbrooke Castle. So with the references in the pocket, I will now break down the tool. We first start off in Unreal, where we get all the input objects, and then they get fed into the Houdini HDA, where we generate the main model. After that, we generate the destruction. We assign vertex colors for the castle shader, and then we scatter various separate brick meshes. After that, the mesh gets fed into my PCG graph, where we add the foliage on the side of the castle wall. So to start off with the modeling, it is divided into 3 main parts, that being the main castle wall, the towers, and the battlements. But this is the modeling process that I talked about, with the main parts of the castle wall being modeled. So as you can see, I have 3 separate parts, that being the towers, the castle walls, and the battlements. And in the end, you will see everything combined together. So moving on to the destruction. The destruction is basically just a Voronoi fracture based on the input destruction cubes that are that gets cut out of the wall. Based on the destruction place, I also add some destruction piles that helps with integrating the wall better with the terrain underneath. Now, if we would import everything into Unreal Engine, it would be very bare bones, and that is because we haven't added the bricks yet. So in this case, I'm adding the bricks to cover up all of my UV seams, to add more detail in the destruction, to create more depth, and it also helps with adding a lot of noise overall. Of course, I didn't model those bricks by hand. I created a procedural system for them. I think in today's climate, it's not worth it anymore to sculpt those things by hand. For me, it was much faster to create a procedural system for this, especially when I need to create a lot of them. The last part the Houdini tool goes through is the shader. In here, I'm adding a bunch of vertex colors that drive things such as the amount of mold and the amount of mass. And this really helps me with breaking up the texture repetition, but it also makes everything a lot more coherent as well. After the Houdini part is done, I fed it into a PCG graph. The PCG graph just samples the polygons and selects the most bottom points of the castle wall, where, for example, vine cards can get placed, as you can see here in the video. One topic I also still want to cover is the Unreal Engine implementation. When you import a Houdini HDA into Unreal, the default interface can be very tedious to work with, in my opinion. So for that reason, I'd like to create my own utility widgets. What this basically means is that you create an interface in Unreal, and then you let Blueprints handle all the scary Houdini stuff behind the scenes. And for me, this is also useful because it helps me combine the two frameworks that I have going on, those being my Houdini tool and the Unreal PCG. And with this system, you can create a bunch of variations, you can see here. I still want to improve a ton. One of the things I'm also interested in is maybe just taking the destruction part of the tool and making it so that it applies to any mesh you can feed it, just not just a castle wall, but that's maybe something for the future. Anyways, thank you all for listening. Just like the other students, I'm also looking for internship opportunities. And now next to Treman.
Hello everyone, my name is Theresia, and I'm very excited to share with you today a project that I've been a part of for the past few months. It's a collaboration between 11 people from students from BUas and ISART with a goal to create a short cinematic. This project started from an idea based on comic books by Pim Bos, who is also our external director, and we've been working together to bring his ideas and visions to life. The story of Treman is set in a colorless, endless wasteland. It's about a lone traveler called Rupert, who roams this world on his mount in search for valuable pieces of machinery and fuel. With his small robot companion, they're learning how to cooperate in order to survive in this hostile environment full of other cyborg creatures also fighting and looking for these resources. It's also important to mention that this story is without a dialogue, and the overall storyline is quite abstract and up to everyone's own interpretation. We started with pre-production before the end of last year, and for the past 2 months, we've been busy with creating the teaser and working on previous scenes for the final movie. We used quite a traditional approach, working from a storyboard to create animatic, learning the craft of movie production on the go. And now, I am proud to present to you the result that we have achieved so far. Now I will share a little bit about the creative process behind this project. This is the current state of our character models, the bodybot and Rumpert. The texturing is fully completed for now. We still might add a few adjustments in future. And here you can see the work in progress of sculpting Rumpert's vehicle, and also the overview of all the characters we are planning to have in the final movie and that we will be working on for the next couple of months. I think I should also mention that this project is set to imitate stop-motion style and recreate miniature-like environments and characters. That approach we try to show in details of texturing to make them more realistic, as well as the motion of characters when animating them. Here are some previous sequences where you can see the progress of blockout animations that have been approved so far, where we try to imitate the stop-motion-like style. Moving on to rigging, the rigs are fully done for the main characters as well as the machines that will also appear in the movie. The environment contains a few assets, some of which we already made progress on, like the fishing stand, remote control, or the bucket. And all these were created using the subdivision method of 3D modeling. Now, we used Houdini to generate this terrain with pipes. The ground textures were also created in the same software for using baked height map from scatter rocks, and then the texture map was further adjusted in Substance Designer. At the top you can see the raw render that was made in Houdini, and then below that is how it was further enhanced using compositing in Nuke, which was also a pipeline that we were kind of trying to research and discover more during this project. Now this hallway that you could also see in the teaser, it was modeled in Blender, but we ran it through an edge limit setup in Houdini. The texturing was also done there, and this scene basically served as our testing benchmark that we were trying to get better understanding of Karma, Solaris, and USD pipeline for our rendering part. And here is an example of how the edge damage tool works. It's also taking into account the individual scale of every object that's inputted there, and basically creates the amount of detail based on that size. And now the rest of the fun stuff were also created in Houdini, such as these vellum simulations of worms that will also appear in the final movie, and also the rope and the cloth simulation that you could also see in the teaser. As for our future plans, we are ready to explore Houdini even further and make use of its soft body and particle tools. We also want to look more into optimization for our scenes and how to implement Karma, Solaris, and USD in our pipelines even better. Our collaboration with Isart, as well as support from Side Effects, will continue. Of course, we are planning to finish modeling and texturing all the assets and characters that we have left, and eventually put it all together to create the final movie, which we cannot wait to show you in future. And lastly, I would like to give credits to all these talented students who've been working hard to make this project happen so that I could share it with you today. And thank you for your attention.